Hi students, and welcome to another video lecture on logic design. In this video, we will continue studying about shift registers. So as you know, registers do nothing more than storing a binary word. The buffer register is said to be one of the simplest registers. Its main job is simply to store a binary word. The buffer register is made up of D flip-flops. You know that in a D flip-flop, whatever is present at the input D is made available at the output Q. So if I give D is equal to 1 and on the next clock pulse, the output Q will also be equal to 1. In fact, most of the registers that we study make use of D flip-flops to store data. A 4-bit buffer register will be made up of 4 D flip-flops. I have labeled them as FF1, FF2, FF3 and FF4. Each flip-flop will have its inputs D1, D2, D3 and D4. Also, each flip-flop will have outputs Q1, Q2, Q3 and Q4. We can ignore the inverted output here, but it is still shown in the diagram. What is important to draw now is the clock signal. I have used positive edge triggered flip-flops here, which can be seen from the arrow symbol on the flip-flop diagram. What makes these individual flip-flops capable of storing data at the same time is that all the 4 flip-flops will be connected to the same clock pulse. So on application of the clock pulse, the word present at the inputs D1, D2, D3 and D4 will be the word which appears at the output Q1, Q2, Q3 and Q4. So in other words, on the clock pulse, D1, D2, D3, D4 will be equal to Q1, Q2, Q3, Q4. This is a very simple register and it is too primitive to be of any use except just to store some data. It can be modified to work a little better. For this reason, we have a controlled buffer register, which looks like this. First, let us understand the diagram before we can understand its working. Notice here that there are 4 interconnected D flip-flops FF1, FF2, FF3 and FF4. Label each input as D1, D2, D3 and D4. Next, label each output as Q1, Q2, Q3 and Q4. Each flip-flop is positive edged triggered and is connected to the same clock signal. Besides this, each flip-flop is also connected to an asynchronous signal called as clear. Remember that this signal is an active low signal since it is denoted as CLR bar along with bubbles on the diagram. When CLR bar is equal to 0, it will force Q1, Q2, Q3 and Q4 to become equal to 0. That is, it will make each flip-flop go into reset state. At each input, there is a small combinational circuit made up of 2 AND gates and 1 OR gate. I am going to name these AND gates as follows: 1, 2, 3, 4, 5, 6, 7 and 8. Besides this, there is a line called as load. And in the diagram, this line is represented using 2 lines. One line is when load is equal to 1 and the other line is when load is equal to 0. The line where load is equal to 1 is connected to AND gates 1, 2, 3 and 4. The line where load is equal to 0 is connected to AND gates 5, 6, 7 and 8. The AND gates 1, 2, 3 and 4 are also connected to the inputs labelled as x1, x2, x3 and x4. AND gates 5, 6, 7 and 8 are connected to outputs Q1, Q2, Q3 and Q4. Now let us see how this circuit works. When load is equal to 1, the AND gates 1, 2, 3 and 4 will receive an input as 1. So AND gates 1, 2, 3, 4 are active and the AND gates 5, 6, 7 and 8 will be inactive, as these gates will receive 0 as one input. From logic of AND gate, you know that an AND gate will give an output of 0 when any one of its inputs is 0. Therefore, gates 5, 6, 7 and 8 will be inactive. Now if the gates 1, 2, 3, 4 are active, then this will allow inputs x1, x2, x3 and x4 to pass through and enter the flip-flop inputs D1, D2, D3 and D4. I have shown an arrow symbol indicating the flow into the flip-flops. And on the next positive edge of the clock pulse, this input will reach the outputs Q1, Q2, Q3 and Q4. However, when load is equal to 0, the AND gates 1, 2, 3, 4 will receive an input as 0. So the AND gates 1, 2, 3, 4 are inactive. But the AND gates 5, 6, 7 and 8 will be active. When gates 5, 6, 7 and 8 are active, the output Q1, Q2, Q3, Q4 will be fed back as input into the register. I have indicated this with an arrow. Therefore, you can say that the data is circulated or retained as the next clock pulse arrives. This means that the contents of this register will remain unchanged in spite of the clock pulse. Therefore, this kind of a register is called as a controlled buffer register. That's all for now. Connect to the classroom for more videos.